Good afternoon. So today we'll discuss mainly single crystal XRD, grazing angle, and synchrotron XRD. In addition, we'll also study X-ray absorption spectroscopy and Newton diffraction. In the last class, we discussed mainly about powder XRD. So there I have discussed that all data analysis, interpretation of results, and fittings. So today I'll just cover that mainly single crystal and the synchrotron XRD. So first coming into single crystal XRD. So the single crystal XRD mainly based on rotating crystal methods. So earlier I told that mostly powder diffraction where this two option, either source can be fixed and detector be movable, or detector or source both can be movable. But here the mainly is a rotating crystal method where single crystal is mounted on a axis normal to the monochromatic X-ray beam. So you have an X-ray source here. From the X-ray source, X-ray beam is coming, and you can see here the crystal is mounted here. You have a reflected that cylindrical film on that, on which you will get that all the diffraction patterns you can see. So with all the diffraction pattern you will see like dotted patterns, then you will convert it to X-ray diffraction pattern. So a single crystal rotate. If the single crystal will be kept on rotating, and then set of lattice will some point make correct Bragg's angle. As you know, we will get a diffraction pattern when Bragg's law satisfied. That means this rotating crystal will keep on rotating. So at particular point, some of the lattice that will be matched satisfy the Bragg's angle, and you will see a diffraction pattern. So by recording the diffraction pattern, both angle and intensity, that means you will take a diffraction pattern where angle 2 theta versus intensity of various crystal orientation, we will get information about shape, size, unit cell, as well as atomic arrangement like bond length, bond angles, and site ordering. So those bond length, bond angles, that is additional benefits that you will get from single crystal XRD. So single crystal XRD allows for absolute structure determination, and you can use them to identify unknown crystals. With a specified chamber, like you can also do high temperature XRD as well as high pressure XRD. Like you can see the in-situ X-ray diffraction pattern, that temperature dependent change in phase. So those things you can study, as well as temperature, as well as high pressure, how the pressure change the crystal structure, those information also you can get. So coming into rotating crystal method, here you have a single crystal that is at the center, that here is the single crystal, and then you hear that we have it involved 3 to 4 goniometer. Like that means you have a 4 angles, 2 theta, that the angle here, the 2 theta that beam to count detector its distance, the 2 theta angle, then also chi, as well as phi and psi. You can see the stage also rotate as a psi omega rotation here, and you have a crystal rotation phi is here, as well as how the distance between the crystal and beam stop, that chi is there. So you have a mainly you can in 2 theta is here. So you have a 1, 2, 3, and 4 goniometer here. So that will mainly decide how that crystal will oriented and diffraction pattern generated. So sample are mounted on a thin glass fibers. Either you can use a epoxy coating or cement to mount that sample on that this brass pin. Here is the you have a pin on that. You have to mount the sample and then adjust XYZ in orthogonal directions to allowing centering of the sample, centering of the sample position. Then you can allow the X-ray beam to fall on the sample. That will get diffraction when 2 theta Bragg's law satisfied. And you have a beam stop here. The role of the beam stop is that it has to block the transmitted X-rays. Whatever the X-ray directly transmitted, so those X-ray will be blocked by the this beam stopper. Otherwise detector, it will affect burnout of detector. To prevent that, you have a beam stopper. And then in single crystal nowadays, that modern day single crystal use instead of photographic detector or 1D detector, it has huge CCD detector, charge coupled detectors are used nowadays. You have to transform X-rays photon into electrical signal, which then transport to a computer. So what will happen? So then only that X-ray fall on the single crystal, and then it goes to you will get a diffraction pattern here on the film. So that diffraction pattern that IK intensity plot, you will get good screw theta. And then you have a Fourier transform that to phase transformation. We do the Fourier transformation. You need to change the, that phase to here, and then you will get an electron density map. So depending upon the material, if you have a high jet material, it will be more dense. If a low jet material, it will be less dense. And like that, you will get different spots. And then this different points you will get, you have to, that pattern at each angle can be used to produce a 3D electron diffraction pattern. Then you can using, putting higher atom at higher jet atom at high density image, so you'll get an atomic model. So mostly it has some limitation though. So in single crystal, we must have a single crystal sample. Like in powder diffraction, you directly use whatever the sample you prepared. But here you have to develop a single crystal, and then only you can go for analysis. And there the size should be between 50 to 250 micron size, and it's optically clear sample. A sample has to be optically clear. In case of powder diffraction, it doesn't occur. And sometimes if a sample has a twin, some defects and all those things, so the twin samples can be handled very difficult in handling. And data collection here, it requires quite long time. You have to go for 24 to 72 hours. Like in powder XRD, you can do an X-ray in 2-minute scan or 3-minute scan. But here you have to get a very good X-ray pattern. You have to go for up to 72 hours. And you can use different software like CellX or OLX softwares are available. So those using those software, you can refinement can be done. You can get a appropriate crystal structure. So this single crystal X-ray was first used, to the analysis of DNA structure. That two famous scientists, that Watson and Crick, they have developed that DNA structure. So they solved this problem by using the X-ray diffraction. So what they did, Watson and Crick combined the information from photo 51 that they got a photographic film with molecular modeling to solve the structure of DNA. What they did, so they have got this type of a diffraction for plane, this type of a diffraction pattern on the film, and then what they did, so here, so they got an X type line. You can see this arrangement is X. So in that X, that indicates that's a helix structure. Then, but they got the 4 diamond shapes that analyze that here. So that diamond shape mainly extends, that indicates long and extended molecules are there. And then in between you can see some pattern space. You can see if you sorry, yeah, you can see here some. If these dots are there, so those dots they are lined up, and they find that the simmering spacing, the distance between repeating structure. As you know, the DNA has a repeating structure of base. So that in between you can see. So here one line and here one line. Those 2 lines are missing. So that missing lines, they told it's a interference of 2 rings are there, and based on that, this Watson and Crick, they have solved this problem, and they got this DNA structure. It's a double helical structure, radius of 10 angstrom, and all this is combining with other information like on the DNA with the sugars and phosphate. So they model molecular modeling with they find out this crystal structure. They got Nobel Prize for this work. And so you can similarly you can identify any unknown structure, like I have shown you on a monoclinic C32H36. It's a cis platinum telluride complex with chlorine. You can see here that this whole structure is been solved by using a single crystal X-ray. So you can calculate the bond angle and cell length. You can see the heavier element platinum is centered here, and these 2 tellurium atom. This is 1 tellurium atom, and this is 1 tellurium atom, and then you have a other chlorine atom here. So you can by putting your heavier atom at the center and other atom is carbon and hydrogen at different place, you can find out the crystal structure. So using mainly single crystal X-ray, you can identify a crystal structure of an unknown compound with the help of analyzing those X-ray data with electron density map. You can able to find out that crystal structure. So in addition to single crystal, so there are other, it's like one is another grazing angle XRD. Like in case of powder, you have bulk sample, like sufficient powder is there, so they can mount on the X-ray surface, that sample source, that sample stage, you're going to get the good X-ray pattern. But you have a thin film, so that is quite difficult in case of powder XRD. you can get some pattern, but you will not get perfect crystal structure or perfect information from the thin film. Since the sample thickness, you have a like this a material, on that you have a coated on a thin layer. For example, on the TiO2 you have coated a silicon or some telluride or something. So this quite thickness is quite small. So on this thickness, if you want to find out that what is the crystal structure of that film, like for example, this is a ZN substrate, on that you have put a TiO2 coating. So this TiO2 information, if you want to get in a normal XRD, what you will get in both information from powder XRD. So only about the surface that top layer you want to find out, you have to do grazing angle XRD. So we'll discuss that, what is grazing angle XRD. So mainly it used for thin film studies. The incident angle is fixed here. You can see you have a substrate here. That green color I've shown the substrate, and on that substrate you have a thin coating of that orange color. This is the thin coating on the substrate. You can see here your theta, the grazing angle is fixed at 5 degrees. Near very less than 5 degrees the grazing angle. Where in XRD you have quite large angle you use. But this grazing angle theta b, you can vary the detector position so that theta will satisfy and able to get information from the top surface that we will discuss. So a GAXRD can be performed to analyze in addition powder diffraction also, but that GAXRD give depth profiling by collecting successive layers. Like in each layer you will get information by using this grazing angle XRD. So it will give information about lattice mismatch between substrate and your film. Your substrate has defined lattice structure and film has defined lattice structure. Those differences you can find out, and you can see the microstrain, how that built up the strain between this interface, as well as orientation of the thin film, whether it's oriented in particular direction or randomly orientation is there. And you can see whether the proper structure, epitaxy or proper structure grow on the film surface. So grazing angle incident, like other instrument like X-ray reflectivity measurement, is possible, where you can do thickness, roughness, density calculations. So in addition, this technique doesn't require crystalline film. Like in powdered XRD or single crystal XRD, you need a this thin crystalline material to see the crystal structure. Here, since you are mainly oriented with the depth profiling or those analysis, you don't need that amorphous material can use in these techniques. So what it used, that in grazing angle you can see, this is grazing angle, if you see, if I like this type of theta value, so you can see the penetration is this much. But if I do a theta like this, you can see that your penetration is this much. So area, that pathway of the X-ray passing through the coating layer increases if your grazing angle is very, very small, and less than 5 degrees, your path length is increases. So because of that, you will get more information about those things. So in grazing angle XRD, you can see here that we're varying the 2 theta, how you can get different information of the different crystal structure. You can see here that in particular, this is one crystal in the thin film. So that is matching with your Bragg's law satisfying or getting a particular one peak. But when you rotate your sample in such a way that that penetration depth changes, and you will get another crystal here, and you will get an additional peak. And similarly, you change that some orientation slightly, that sample orientation, you will see another crystal on which that X-ray beam is falling, you will get additional peak. So by that way, even in a thin film, you are able to get this type of depth profiling. So those are mainly useful for phase identification, stress strain measurements, as well as dealing structure analysis can be possible using this type of crystal structure. And then here the instrumentation mainly involved, you have a sample here. You can see the sample stage is mounted here. You have an X-ray source here. From the X-ray source, the X-ray is coming and falling on a Bowell mirror, and that mirror is mainly it will help to focus that. It's a very low angle. You have to use a mirror, so that mirror is falling on the sample. Its angle is here is less than 5 degree in this case, and then you can see that then sample in the diffracted sample will fall in a monochromator, and then from that monochromator it will go to the detector. So finally detector will detect that and will analyze, will get a pattern. So mainly it's instrumentation part is similar to that of normal XRD. You can see here the difference between a normal conventional XRD pattern and a grazing angle XRD pattern. Here you can see that this is an unattached the TiO2 photocatalyst thin film on a substrate. So you have here in that you have a thin film. On that you have a TiO2 structure is here. This is your TiO2 structure. On that TiO2 structure, if you go for an X-ray, conventional X-ray analysis, you can see that is a very small peak is here, and you are not getting any other peaks, only small peak in case of the conventional XRD. When you go for a this type of low angle grazing angle diffraction pattern, you are able to see that the unattached phase. You can see how intense unattached phase you are getting here. In addition to that, you are getting also information from the other peaks which you have absence in case of conventional XRD. And similarly, you can see the right image of a solar cell that you can see in case of solar cell that more additional peaks you are able to getting here. When you have a theta2 theta scan here, and you have this conventional XRD that 100 plane and that 102 plane, those peaks are very weak peaks are here. But when that omega theta omega value is 0.1 or 0.5, it's very low grazing angle, you are able to get, you can see how intense peak you are getting. So mainly normal XRD, large portion of diaphragm comes from the substrates. Like here, the substrates background will come because your normal XRD before it may be go inside. So that's why you may get some information about the substrate. But in case of grazing angle, it's mainly diffraction keep from the thin film. Here the path length will increase here, so that will give more information. So you can see here it is a thin layer structure of molybdenum, then a solar thin film gallium, this thin film, and then on surface you have a ZNO. So you can see by varying the grazing angle 0.25 to 1 to 2, you can see how the information is coming. When you're 0.45, but that CIGS solar film you are taking, you can see that some additional peak are missing here, and all these peaks are missing here. But whenever one degree, that depth profiling is more, like you can see here, where beam is your area of interaction is this. Here your area of interaction is increasing, and here you are increasing further area of interaction. So from that you can see some additional peaks you are getting. So depth profiling is possible by varying the incident angle in case of grazing angle XRD. You can see here you have a titanium nitride, and then you have a first layer is titanium nitride, and second is titanium carbide, then titanium nitride on a tungsten substrate. Now, here you can see you have an interface here. That interface is mainly TIN and TIC. So here you will see the profiling of this interface, what is happened on TIN and TIC. So there is an intermetallic phase in between this. So here in this zone, you will get a TICN phase. So that to analyze that phase, you can do a grazing angle XRD. You can see when you have a bulk that 2 theta is 2 degree, and you can see this TIN peak is you are mainly showing this TIN peak here. And when you have a then the TIC, that interlayer, that middle layer here is very weak, and that when you angle that theta is increasing, you can see that the peak intensity is increasing, as well as you are getting one additional peak here and one additional hump you can see here. So this hump is TICN. So that is clearly showing you have an intermetallic phase in between. So you can use the grazing angle XRD to analyze the intermetallic phase. And here you can see that that you can also measure the residual stress or strain built up in a material. When you have a stress, you can see that this left side image, that yellow one. So you have a normal, no stress is applied on stress sample, you'll get a peak position here. When you have stress, either tensile or you can compressive stress, what will happen? So your enlargement is possible because of stress, that peak is shifted from this position to this position. So those type of residual stress can be determined from this. You can see here, this is a bismuth titanate XRD pattern of a strontium titanate on substrate. It has grown on a bismuth titanate is grown, and you can say the only 004, 006, 008, they are all same family of peaks you are getting. So that indicates that these are mainly the thin film is highly oriented and it's grown in a particular direction. So those orientation effect also you can able to get in using grazing angle X-ray diffraction techniques. So in normal X-ray diffraction or in this grazing angle X-ray, so you use a source of copper K alpha that uses a normal XRD source is used. In that case, that the brightness of the X-ray as well as flux of the X-ray is it's not that high. So when you go for a synchrotron radiation, that you can use energy from a synchrotron. So here that brightness and the flux is quite high, 10 to the power 12 order high to 13 order high in case of synchrotron. In that you will get much better information. So that we will discuss here. So if you go for a synchrotron, which is XRD, so in synchrotron what is mainly used, you can see this type of rings from the magnets are there, ring structure. So synchrotron is a ring which uses magnets and electrodes to accelerate the X-ray or light nearly speed of light. So generally what happens in case of, as I discussed that X-ray tube, we have a, that potential difference there. So that potential will enhance the, kinetic energy of the electron. You will get quite high kinetic energy of the electron to fall on the copper target. But in case of, the synchrotron, you use, lots of bending magnets are there. So you can see it's a circular ring. On the circular ring, when the electron beam will flow like this, what will happen? So each step, so it has some electrodes and magnets are there that will enhance the speed of X-ray to the equivalent to light. When such a high kinetic energy can be attained in this case, and synchrotron radiation is an Arpan's collimated light source of high intensity. It is a collimated, highly collimated, monochromatic, and high intensity is the source. And in synchrotron produce X-ray that are monochromatic and very high energy, and it's right energy for light element like carbon and oxygen. If you go for carbon and oxygen, those things analysis is not possible in case of this normal conventional XRD, but that energy is sufficient for the element like carbon and oxygen. In addition to the conventional diffraction pattern, you will be able to get atomic pair distribution analysis, that PDF. So you can see how the electron distribution is there. So that will analyze, even you have a diffuse spectra that is scattering, like in amorphous structure, you can also get some information by using single crystal XRD. So this enables one to find out the bond distance, coordination number, the material that is even not, they are not fully crystalline. So single crystal XRD has many advantages and in structural characterization of materials at atomic and molecular level. And you can use a trace amount of element to get this XRD pattern. So in case of conventional XRD, it's quite large quantity. Here, even a small quantity of sample you can use since your X-ray flux is quite high, you can use them to analyze. So in case of synchronous radiation, you have a first thing, you have a high brightness. So brightness means the brilliance of the X-ray from the third generation source is 10 to the power 15 to 10 to the power 12 times more intense than from the laboratory sources. In fact, the intensity is quite high. Second thing, that is highly collimated. The synchrotron light is parallel, and therefore, it's spread normally. As it propagates, you will get highly, this monochromatic light, X-ray. And then here you have a wide range energy spectrum. Here, in case of X-ray, you have a fixed wavelength in the conventional. But here, you can, radiation includes a wide range of energy from infrared to hard X-rays. So allowing an optimal wavelength selection to reduce the absorption either in the sample holders or in the sample by varying wavelength-based experiments. So you have a wide range of variation in the energy spectrum, and also a short pulse time structure. Like, it's a short pulse time structure allows the process resolution is quite high on the time scale. And you have a penetration depth is much higher in case of, laboratory conventional X-ray. So because of these things, synchrotron X-ray will give better ray diffraction pattern. You can see here the source is here for electron beam is circularly flowing, and then finally coming out. The collimated beam is going through the slits and mirror. It falls on the sample here and mounting on the crystals. So here is the sample. So and then it focused mirror will go to the, finally it will different types of mirror will use, and finally it will fall on the sample here. And then the sample we have a detector that will detect the diffracted beam. So in SR, beamline refers to the instrumentation that carries synchrotron beam experimental to end station. This is whole process is called beamline process. So because from here to here it goes with different optical pathway. It incorporates monochromator, slit, mirror, and other devices to finally to focus on the sample. Here mainly sample is mainly placed in a capillary geometry in a thin film, then a capillary tube sample used to mount it, because that, capillary tube, it's easy to mount the sample as well as, focusing and centering the position is quite easy in case of capillary tube. So that's why they use in a capillary source here instead of a conventional XRD. You use on a substrate, on a plain substrate here you use capillary press. So here the synchrotron has a major advantage that you will not get it being its highly monochromatic, high flux and highly collimated beams. So you will not get any K alpha 2 radiation. So initially the conventional XRD, what you get a peak like this type of splitting, that K alpha 1 and K alpha 2 you get. So here this K alpha 2 peak will be eliminated if you use a highly monochromatic this synchrotron radiation. And then the signal to noise ratio is much higher, and the noise will be substantially reduced, and high angular resolution. You'll get a better information by allowing analysis of complex structure. You can use using proper refinement, even the peak broadening effect, those two parameters you can able to identify using synchrotron radiation. So here that here detection limit is 0.1%, weight percent, whereas normal XRD below 2%, it's quite difficult to detect if you have a solid, structure like something doping into another material. So those dopant concentration to identify is quite easier in case of synchrotron radiation. And you can do both in situ and ex situ measurement. Here during the process, you can use high temperature experiment, you can use pressure-based studies. So those are possible in case of synchrotron radiation. You can see here, if you see the conventional spectra, that LXRD, laboratory XRD, and SR-XRD, the synchrotron XRD, you can see that in case of this synchrotron XRD, some additional peaks, those small peaks here, the mullite is a ash sample, that ash sample, coal fly ash, that was analyzed using two techniques. You can see some these peaks which are not quite detectable in case of XRD, normal XRD. So these peaks you can see that quite high intense peak you can able to get in case of some also in addition some other peaks. So those things you will get if you have a synchrotron radiation, that more information you can get. So diffraction peak obtained from a synchrotron XRD are stronger and more well resolved than those of laboratory XRD. Especially you can detect those minor phase like this calcite here that you are not able to get in this case of laboratory XRD, and this manganite. So those type of information you will able to additional trace element, whatever they are, those you can find out. You can see this is a temperature experiment performed in a synchrotron radiation. You can see that at different temperature, how that as the phase is increasing, the intensity, that peak intensity increasing, that indicating that particular phase is tetragonal to cubic phase transition which are occurring here, and those information you will able to get in case of synchrotron radiation. You can see how the additional peak you can see at 300K you have both 001, 100 peaks is there. When you increase the temperature, you can see only 100 is from predominant, where other phase is completely missed. So this type of information you can able to get from a synchrotron XRD. And this whole thing is performed by using Indus 2 synchrotron radiation at RRCAT. So you can using, and this is because that high energy, the energy higher than 500 keV is beneficial for this in situ experiment. So it's quite high energy that you are using. In case of high pressure also, you can see that with different compressive or tensile stress, this is a 3G, T2, that material which are different pressure 0.3 to 25 gigapascal pressure is applied at room temperature. You can see with the temperature how this particular phase is developing and peak shifting which is occurring, as well as particular phase is developing the hexagonal structure with gradual shifting in peak to a larger angle increasing pressure. So how when the pressure increasing, so that the peak is shifting towards the right side, and then you can get that how the volume of the is changing and the lattice parameter things are changing. So those type of composition like information about shrinkage of lattice, compression, all those things can be get from powder. So nowadays, even synchrotron is possible, combination of different imaging and spectroscopic technique with that. So by combining diffraction with imaging as well as spectroscopic technique, you can get more information. For example, you can use that synchrotron experiments can be combined with, Raman spectroscopy and X-ray absorption fine spectroscopy. So by combining these two techniques and this energy dispersive time result spectroscopy and XRD, can be combined to get additional information of this type of structure. So you have a complex structure, so that thing can be analyzed by using multi. In the conventional XRD, you have only X-ray source there. You can do only X-ray crystallographic analysis. So in case of synchro radiation, since you have a wider wavelength, that energy variation is there, you can combine multiple techniques. So with the mapping the chemical, physical, and crystallographic properties of sample in 2D and 3D using smart combination of diffraction, imaging, spectroscopy will give us better information. So, for one example is X-ray absorption near-range spectroscopy that we'll discuss now. X-ray absorption spectroscopy where X-ray is getting absorbed, and then during that absorption, that photoelectron is coming out, how that electron interacting with the surrounding atoms. So that will give this is main basis of the X-ray absorption spectroscopy. So there we have a X-ray absorption near-range spectroscopy, an extended absorption fine structure. Those type of in-depth analysis can be done using this type of synchrotron-based radiation. So before going into X-ray absorption spectroscopy and fluorescence spectroscopy, there is any questions on single crystal XRD or synchrotron-based XRD or Grazing XRD, you can just raise some questions if you have. Otherwise, we'll discuss the next part. Just if any questions are there. Okay, if there is no question at this on this part, so then we'll discuss the second part, that is on X-ray absorption spectroscopy. So here that X-ray absorption spectroscopy, I'll discuss that X-ray the extended X-ray absorption spectroscopy and near-edge spectroscopy as well as some X-ray fluorescence spectroscopy. So whatever I discussed so far is mainly X-ray diffraction techniques, that small powder diffraction, single crystal XRD or synchrotron XRD. So I discussed the phenomenon of diffraction. So now we'll talk about X-ray absorption and X-ray fluorescence spectroscopy. It's, as you know, that the intensity of X-ray beam passing through a material of a given thickness, X, if the material is here, the thickness of the X is passing through this material. So absorption coefficient is determined by this equation I equal to I0 e to the power minus mu X. So that mu is nothing but it's a linear attenuation coefficient, or we can express in rho by mu by rho, that is mass absorption coefficient. So using this mass absorption coefficient of material, that the absorption capacity of a material for X-ray is mainly decided by this mass absorption coefficient, and it's a mu, that is the rho z to the power 4 a to the power 3. So here E is mainly that X-ray energy. What is the X-ray energy source is huge, and Z is atomic number, and rho is density of the material, and A is atomic mass. So mainly that this mu, that absorption mass absorption coefficient is mainly depend on these 4 parameters. And X-rays are absorbed through the, as I discussed, through the photoelectric effect. X-ray are absorbed the material. If you see here, so X-ray absorption occur like you have a high energetic beam can capable to remove a core electron. You have a core electron here. So when you have an X-ray, incident X-ray falling on this material, it is quite sufficient high energy. That means that kinetic energy is much higher than that of the binding energy of this particular electron with the nucleus. Then what will happen? So this electron will simply jump from the one state to the continuum or unoccupied states. So here you will get a vacancy will create one core hole will be created in this case. So excitation of a core electron into the higher unoccupied state or a continuum is mainly possible whenever X-ray source is common fall on this. So by the photoelectric effect, this will be go to the higher states. You can see here that if you have 1s electron is here, the Bohr atomic order K, L, M, N cell. So if a 1s electron can be moved to the continuum, K cell electron, or in L cell also, these three are L cell. So L1, L2, L3, three stages are there. So any of them can be go to the unoccupied states. So mainly, so it gives it sensitive to chemical state and local environment, how the coordination of that particular electron here that coordinated with the nucleus and its chemical state. So those things will decide the absorption capacity of a particular X-ray and removal of the core electron to the continuum stage. So if you see that when necessary energy, that binding energy of a core electron is attained, like unless until the binding energy, if you can't overcome the binding energy, the electron will not knock out to the continuum. Once the binding energy achieved, the electron will move to the other levels. Once it moves from here to here, it will move. So what will happen? The absorption edge, you can see that what is the absorption energy of the mass absorption coefficient. It's slightly, see there is a enhancement in this case. And similarly, when L and M cells, so you get this type of absorption edge you will get. So that will decide each edge occur at its own critical absorption wavelength. Like in X-ray, that you have a particular wavelength like that. Here also each absorption, that is the edge you are seeing here. So this particular edge you are getting here. So those edges are dependent to a particular material, has own its element, unique to each element. So that is the basis of X-ray absorption spectroscopy. So it gives information about bonds, types of bond, what type of bond is there, is bond strength, bond length, as well as nearest neighboring atom, as well as defects and disorder. Those information you can able to get in this. You can see here Fe, that you have a K alpha A, K edge of Fe is 7.1, where nickel is 8.3, copper is 9.0, molybdenum is 20 kiloelectron volt. So this difference is much in between. They have a unique characteristic, like so you can, if you identify particular K edge, then able to identify the materials also. So K edge are mainly leveled to the cells from where the core electron is originated. If it originates from K orbital, and like K cell, then it will call it a K edge, or similarly L cell is the L edge. So L1, L2, L3, those edges you can get. So in case of X-ray absorption spectroscopy, what happens is that modulation of X-ray absorption coefficient at energy near and above an X-ray absorption edge. Like this is the absorption edge. This is the absorption edge, that particular material. Here the absorption edge, here is the L absorption edge. At this area here, how the energy, the mass absorption changes the photoelectron energy, photon energy. So that will give you, you have a near the absorption, near just above as well as here. That means at this side you will analyze. This is the absorption edge. So you will mainly see the analysis of this part and this part to see how this information you can get. You can see if a spherical electron is here, that wave will be propagated from here in a spherical in nature. So this is in the spherical way, the waves will propagate. So based on the de Broglie equation, and this wave, when the X-rays fall on this, so it may fall on one particular atom, and then that wave generated here will interfere with the other electrons is present nearby this source. So that means there is interaction between all these electrons is possible. So here that lambda de Broglie equation, lambda is h by p, you can express it in wave vector k equal to 2 pi by lambda, and in this equation the kinetic energy Ek equal to E minus E0 at the initial energy. So you'll get h nu minus E0 with combining this equation, get an equation k equal to 2 pi to the a by h whole square 2m into h nu minus E0. So here E0 is the threshold energy, which the amount of energy photoelectron need to promote an electron to the continuum. From the hole to move to the continuum, the minimum energy is E0, and E is the X-ray energy, that incident X-ray energy. So if you have a kinetic energy of E, that is that h nu minus E0. So here, since EXAFS is mainly an interfering effect, it depends on the wave nature. So you can see here that it's a diffraction that you are dealing with, only diffracted the X-ray beam. But here the X-ray EXAFS, here that whatever the X-ray is observing here and knocking out that electron to outside. So there is a interaction between that the interference effect of wave vector of one electron with the other one. So that's why it's more easier to express that X-ray absorption spectroscopy in terms of wave number rather than energy. So we express in the wave number K, in the term of wave number K, we express X-ray absorption spectroscopy. Like you have a core level here, X-ray is falling here. There are three phenomena can be possible. In one case, low energy, the energy is not that much sufficient. So not having enough energy to completely leave the atom. So atom will just move from here to the unoccupied space here. So that is the K equal to 0 here. So it will just go to the unoccupied state at low energy X-ray near edge spectroscopy. You will get information about low energy absorption. Or you have energy that is much higher, like you have a very high energy, and that occurs, and immediately it will go to the this on beyond the atom. So that will happen that continuum will go escape into the continuum, and you just get information about occur scattering process between the neighboring atoms. Like here, the weak and back scattering occurs. So that electrons will be completely go out of that system, and there is a weak interaction. So that will give you how the two electrons interacting. If it's in between, you will get just enough kinetic energy able to escape into the continuum. Then here, it will just go into the continuum. In that case, multiple scattering is possible between the neighboring atom. And you will get, in that case, this distance between that XANES, where you will get that X-ray absorption near edge spectroscopy that we discuss. You can see here, you have a observing material here, that is the core level, the sensitivity of the core level. The X-ray is falling here, then what will happen? You will get a particular, because of that absorption, and that electron will move to the photoelectron will move out, and what happened? So your the X-ray, that wavelength is interacting, will get a particular wave pattern, K wave pattern here. So you can see when the absorption edge will reach, so that it will go like this, the absorption probability with energy, and when the absorption edge reaches the particular wavelength, that the energy will achieve across the binding energy, it will jump into the higher state, then it will continuously increasing. So here, once E is large enough to promote a core electron to the continuum, there is a sharp increase. This is a sharp increase. So here, the nucleus of a particular electron here, once it go out, so what will happen? You will see there is a sharp absorption exchange. So isolated atom that has mu E with a sharp spectra, you will get probability the core binding energy and is smooth of Fe. You can see here the smooth curve is here. So if absorption probability mu E versus E, if you plot, this is nothing but mu E versus E. If you plot, you will get this type of spectra in case of absorption spectroscopy. But whenever there is another atom, so this is the observing atom, the X-ray is falling on this atom, and then the waves is generating here because of this interaction of the X-ray, and then the wave vector is generating here. That wave is interacting with the scattering atom. Another atom is nearby, another atom is there. You can see here is a blue atom 1 and red atom 2. The wave front of the blue atom will interacting with the wave front of red atom. So what will happen? And then there will be a phase, the change of fine structure information will get here that, this absorption occurs, and then because of that absorption, then thereafter you will get this type of, spectral information. So EXAFS is an interference effect of photoelectron with this itself due to due to presence of neighboring atom. So if there is a neighboring atom, so that neighboring atom, the amplitude of the backscatter of a photoelectron at the observing atom will vary with E. So this wave vector, what is going here, so that will interact with the backscattered wave vector of the second atom. So you'll get some, so you're going to be sum of both these, you'll get a fine spectroscopy. So typically X-ray absorption spectrum that you will get, what will to mainly the shape of the edge and the pre-edge resonance are characteristic. Here you can see this is the mu E, that absorption coefficient versus energy is plotted. You can see. So here one peak you are getting and another is main absorption edge is here. So this is called pre-absorption edge or this is absorption edge. So this will give you mostly electronic information of the material like oxidation state, coordination number. Those information you will be able to get from this particular zone. So beyond that, the geometric information you'll be able to get whether it's tetrahedrally coordinated, octahedrally coordinated. Those information you'll get, extended X-ray fine absorption spectroscopy. So mainly they can use it as a fingerprint to identification of local structure. Like normal XRD, you can able to find out that that phase formation or the crystal structure. If you want to find out the coordination number or oxidation state, though oxidation state you can use your X-ray photoelectron spectroscopy, but coordination number, like how the atom is coordinated with a neighboring atom, there is coordination with the coordinated with 6 atoms, 12 atoms. So those information you can able to get from the XAFS study. So here the analysis of photoelectron scattering by surrounding atoms near and above core level. This is the short range interaction that will give X-ray absorption pre-edge extending to a few electron volt. Here this is very few electron volt, that is the absorption edge, and beyond that recommended by local density states in the vacants observing atom. The region is very sensitive. Like for example, if oxidation state like chromium existing +3 and +6, vanadium +4, +5, iron +2, +3, those type of oxidation state identification is quite easy by this absorption spectroscopy, because this band edge emission will be slightly with +2 and +3 charge, it will be vary. So you can see in case of X-ray absorption near edge spectroscopy, here one atom, blue atom, is interacting with the green as well as 3 red atoms. So there is a multiple scattering occurring between multiple interaction that's sensitive to multiple interaction scattering path. So that will give you sensitive information towards the symmetry of neighboring atoms, that is coordination number, valency band structure. So this band edge, this to this structure, you'll be able to get the information about coordination number and band structure. That is mainly region 30 to 40 electron level. Like here you have a 1160 within 30 to 40 electron volt in this row. That you will able to get this information. But in the extended X-ray absorption fine structure, that is beyond that 40 to 1000 in this region, 40 to 1000 electron volt path edge is a quite subtle wavelength. It mainly interact with one atom with a neighboring one. So it's a 1-2 interaction rather than multiple interaction. So dominated by single scattering paths, and it's sensitive to the immediate local nearest neighbor. What is the nearest atom? It will show information about the nearest atom rather than symmetry of the neighboring atoms. It will just show the which is the nearest atoms. If you see, you can see XANES that the blue, red, green atom is interacting with blue and red. How the overlapping of these three. If you have a sufficient binding energy there, to overcome the EK, you will able to get the interference is mainly dominated by the multiple scattering which occurs here. 1, 2, 3 scattering will be, I have shown here. So that can give you, indicator of kind of bond symmetry, such as tetrahedral or octahedral information. Those things you can get, and also it can give indicator of the valency band structure, valency state. It also used in electronic band structure calculations. This type of information you can get here. But in case of XAFS, it's 1-to-1 interaction here. So that will mainly amplitude photoelectron falls in that 1/r² relation, where r is the scattered the distance. You have an observer here. This is the X-ray is falling here. This is the observer, and this is the scattered. What the X-ray wavefront is producing here, it's scattered by this. So this distance is called r. If it's the amplitude of the scattered photon fall in 1/r² relation, you will get exact information that it's inelastic loss, thermal fluctuation, mean free path, then multiple scatter contribute significantly. Like here, in order to XAFS analysis, the multiple scattering sometimes interfere. So for this reason, scattering is mostly limited to atom or ion vicinity of 0.5 nanometer. Those atoms are quite close to the nearest neighbor. So those information you'll be able to get. And the phase and amplitude of a best scattered photoelectron depends on the factor, like whatever the wave front is coming here, when it is the scatter rate will return back. So that will depend on type of bonding of atom, energy change of the surrounding potentials. So on that information, it will depend on the backscatter factors. So thus the numerical analysis of XAFS field information about immediate local environment, surrounding and observer atoms or ions. So if you want to interpret this structure, so how to analyze is not easy. The XAFS analysis or the XANES analysis, the interpretation part is quite difficult as compared to normal X-ray diffraction or other characterization techniques. So mainly you use that FEF is a software that is commonly available to use to analyzing this type of spectroscopy. I'll just broadly discuss the steps involved in the interpretation. Like once that absorption occur on a material, so here the material is observed, you will get I intensity pulse, and I0 is the initial intensity, I is the after absorption. So that is the equation, mu E, you can express in terms of lambda like this. So here you can see this is a absorption spectra that you are getting. So then the fine lines are there. So here this is the pre-H line. So here to here that is a sharp H change, particular that mu E versus E plus. So this to this the sharp transition, and then if you have a straight line, you draw a straight line here, post-H here straight line, and then this background, whatever distance, the delta mu 0, you subtract, and then you get this background corrections. So then you isolate that XANES, that what happened then, that this part, so this part then you isolate, remove, you will get mainly the initial XANES part. You get the sharp band edge, those information you will able to get if you subtract the background correction and then post a subtraction. You fit a linear here, and that's when you subtract, you will get mainly that this particular absorption H. So now that to calculate E0, then this equation that K equal to this equation E H nu minus E by E0, so that E0 value when you derivatize this first derivative, where the E by E0 is the maximum first derivative that you put here, then you are able to get that H nu, that the wavelength of the, that the photon energy of the incident X-ray, and E0 you can calculate from this, and you will be able to calculate the K value here. Once you get the K value, then you can use further analysis that we'll discuss. You will be able to get the information about the oxidation state and coordination number. You can see here, on example, I have seen chromium in +3 and chromium in +3. Here is octahedral geometry, here is tetrahedral geometry, here is octahedral geometry. So those things you can find out from this oxidation state. You can see in case of chromium in +6, you can see there is a strong absorption edge you are able to see here. But in case of +3, this absorption edge, the pre-absorption edge you are not getting. So this copper, chromium 3 and chromium 6, so dramatic dependence oxidation state that depend the coordination chemistry. Here it is octahedrally coordinated, tetrahedrally coordinated, chromium 6 plus. So those type of information on the spectral information you can able to see how that pre-H transmission 1s to 1s electron is transmitted to 3D here, that you are getting a chromium. In case of that, you are getting a P. So those type of information you can get. You can see in XANES also. You can one example here. There is chromium metal, chromium oxide, and then chromate. See, calcium chromate is here. You can see in calcium chromate in all these three that is mainly oxidizing chromium in +6 stage here. So in case of +3, you can see that pre-H, strong pre-H absorption you are getting. But when you go to chromium oxide or chromium metal, the pre-H absorption is not there. So that you can identify whether it is in +6 or +2 state. And here in case of this, you can see this absorption edge, it's also shifting to the lower delta E when you have a tetrahedrally coordinated in comparison to octahedral geometry. So based on that, whether the coordination chemistry, I have shown just one example. So other material, whether it is octahedrally coordinated, tetrahedrally coordinated, those information you can able to get from this spectra. Absorption spectroscopy. So to interpret the XAFS analysis is much difficult than that XANES. Here the K equation is the web vector equation is this, and then that will be expressing a phase relation of this type of relation. The fk and delta k, those are dependent on atomic number and sensitive to Z of the neighboring atom. Since it's an interaction between two atoms and nearby one atom with the other atom, direct interaction. So one interaction here, what even happen? So that F and T depend on the atomic numbers as well as sensitive to the nearest neighbor, Z value of the nearest neighbor. Like for example, copper and nickel is there, copper and palladium is there. Palladium is heavier Z, so there the interaction is much more. So here the Fourier, you have to do a Fourier transform from K space to real space. So all web vector, it's expressed in a K space. Then you by using Fourier transform equation, you convert to R space. Then once R space you obtain, then you have to do in model fitting by using this type of IIFE fit. So program you can use that, or you can calculate that all the information about that main free path and coordination numbers, all those information. So here I have one example I have shown. So you can see this is the common spectra, normalized experimental EXAFS spectra of a zinc H of a ZNO material. This is ZNO, this is 2% this manganese and 2% dysprosium doping, and this is 6% dysprosium doping. Here you can see how the absorption H changes. So first what you have to do in EXAFS analysis, first convert mu E versus E. So this is mu E, the mass absorption coefficient versus photon energy. So this you have to convert to chi E by using this equation. And then once you get chi E, then subsequently chi E versus E data will be converted to chi K, that is energy to web vector relation chi K versus K per photoelectron wave number is this. So once you get this information, you can see, so initial equation was like this. So after performing this analysis step, so you will get this type of spectra case, chi K versus chi K, you will get. So K or K versus chi K or chi square, K square or K cube, you can plot. Once you multiply higher order, you will get better information. So finally chi K versus K, you can plot and generate an EXAFS spectra. And from this spectra, so becoming the peak position, all these things, you will be able to find out that, that bond distance, coordination number, or Digital factor, all those information you can be able to get in this. So there is something stuck here. And minimize it. It's stock, it's not moving. Slide is not changing.
Just one slide. Just one slide.
Because there are some technical problems. So you after this, performing this all this analysis, you can see with fitting, you can calculate it that different parameter, how the ZNO bond length and the neighboring atom. So those information you can able to get how much cobalt of the ZNO, so bond length of ZN, and those information you can able to get. So you, from the peak position here, that. So here in case of this 3 nearby 3, so those thing information you can able to calculate in this information. So So far, what I have discussed is X-ray absorption spectroscopy. So we'll discuss next that X-ray fluorescence spectroscopy is equivalent to X-ray absorption. Only thing is in case of X-ray absorption that that the electron is a hole you have created, and electron is moving to out continuum or unoccupied state. But here in the case of fluorescence, that once that this process will happen, that it goes outer, so excited that you create a core hole will be relaxed to background state. This hole is in excited state. So once it to relax it, what happens? The higher energy that the other level, higher energy levels, electron from the higher level will fall down here. So it will occupy this position. And what are the excess energy? Since the core is hole is lower energy, and this was the higher energy. So once this electron fall here, you have an excess energy. So that excess energy is limited as a fluorescent X-ray, and it is specific to a specific element, and it gives both information about qualitative and quantitative information you'll be able to get in case of X-ray fluorescence spectroscopy. So you have some specimen here. So the X-ray from X-ray source, light will come and fall on the specimen, and from here it will go analyzing crystal. You have an analyzing crystal here that is not there in X-ray diffraction pattern. On the analysis, fall on the analyzing crystal, and whatever the analyzing spectral X-ray will be generated, it will go to the detector here. So here is the detector, it will go to the detector. So by using that same, that n lambda equal to d sine theta, so you have a X-ray source is here, and then a specimen is there, but in addition you need an analyzing crystal rotate to reflect each wavelength to satisfy Bragg law. Whatever the fluorescence characteristic X-ray is emitting here, so that X-ray will be satisfied with a particular that rotating crystal here. Once that particular Bragg's law satisfied, you will get that that wavelength will come out. So that will detect. So XRF is diffracted by a crystal at a different angle, different phi to separate out lambda. So here is that you have an angle phi, so that will identify, separate out each wavelength. So here mainly two types of XRF spectroscopy is possible. One is energy dispersive, where it can be elements can be identified and the basis second to the energy, or it can be wavelength dispersive, where they can be calculated, which is separated by the wavelength. So it is used for element analysis. You no need a crystalline material here. Whatever the material that's mainly used for composition analysis. If you have a copper oxide, so you can calculate what is the percentage of copper, what is the oxygen of concentration of oxygen. So those things you can calculate here, mainly used for composition analysis. Here you don't need any sampling, or it's a non-destructive technique and very fast process. So all the elements in the samples are excited simultaneously. Here you have multiple elements there, so all elements will excite simultaneously. The detector will detect, separate them, all the elements. So here the better efficiency, in case of EDAX, you will get detected without being separated. But in case of WDA, WXRF, the better resolution, but you have efficiency is much better. So what happened in both cases, you will able to get whether you use EDXRF or WDXRF, you will able to get the information about the composition. All elements analysis is possible except hydrogen, helium, and lithium. So these are the three elements that you can't detect using this X-ray fluorescence spectroscopy. So the detection limit is very, very less, with 0.1%. You can define evaluating spectra, whether that K alpha, KL spectra is there. So Compton scatter effect, or whatever the sound, this radiation, all those information you will get, and when you analyze it with energy or wavelength based, you will get that particular phase percentage present, and compare the area under the peak, you can able to calculate that particular percentage. And but you have a lot of interfering effect that will overlap, that has to overcome. That is one is spectral interference, like K and L line of additional elements are sometimes quite similar, so they overlap. So those things has to be separated out. And environmental effects like light element like sodium to chlorine, they emit weak fluorescence. So that fluorescence things which can easily accumulated by air or interference with argon in the atmosphere there. So those things has to be able to overcome. And there is a matrix interference like absorption of enhanced element, like some X-ray which produce that fluorescence. So that fluorescence absorbed or scattered by the nearest element. So because of that, you will get X-ray of one element excite the other in the sample, therefore signal is enhanced. So those type of matrix interference you have to separate out, and then finally you will able to get information about this type of spectra you will get. So you can identify whatever that phase present in the X-ray absorption. So like this is an example of NIST standard milk powder is there. So in that milk powder, we have to find out the carbon, calcium, argon, or concentration, potassium. So all these element concentration you can able to find out using this X-ray fluorescence spectroscopy. Very easier technique in comparison to any other chemical composition analysis technique. Is straightforward to give you the percentage of the elements present in the sample. So I'll just discuss next 10-15 minutes about neutron diffraction. So far what I discussed is mainly based on X-ray based technique, that's X-ray diffraction, single crystal as well as conventional powder XRD or synchrotron XRD, as well as X-ray absorption spectroscopy, where I discuss XANES and EXAFS, and then I discuss X-ray fluorescence spectroscopy. So those are mainly X-ray based technique. So now we'll discuss neutron diffraction. Here it is complementary technique of X-ray diffraction, but only thing is your source is different. Here instead of X-ray we are using neutron as a diffraction source. Neutron diffraction. Neutron is the main thing. So as you know, the neutron have a spin half and it has zero charge, but it has a magnetic moment of 1.913 mu n. Since it has a magnetic moment, so because of that, the neutron interact both ways. There is a nuclear interaction and there is a magnetic neutron interaction. So neutron interact the nuclear, that's nuclear neutron interaction. So there is no form factor dependence. It will not depend upon the form factor. And it's mainly elastic that will be used for diffraction studies, crystal analysis. It's inelastic, like you can excite, you can use for phonon vibration analysis, or in addition that since it's magnetic, you will get a magnetic neutron scattering. So it has a dependence on the form factor that is fall faster than the X-rays. So X-ray, as you've seen that form factor, atomic form factor F is proportional to sine theta by lambda. So that case is F versus sine theta by lambda. So that X-ray is falls like this. So neutron is falls much faster. This is for X-ray. This is for neutron. So in form factor, neutron falls much faster. And then this similarly you will get all this elastic diffraction. So those will be used for analysis. The most form factor that F you will get intensity F square intensity. You have to read some sum of neutron magnetic interaction and neutron magnetic interaction and nuclear interactions. So neutron is nucleus is here, and the nucleus neutron is a small portion. So it has a that quite small that the nucleus is here in comparison to electronic cell. So neutron has a thermal energy of it is the 10 to 100 millielectron volt and wavelength of 2.8 to 0.9 angstrom. So mainly thermal neutrons are therefore useful in studying the atomic position correlation in condensed matter physics. So it's atomic spacing is equivalent to that of wavelength. So you use them for like similar to XRD, you can use them from diffraction analysis. So neutron diffraction determines the atomic as well as magnetic structure of the crystalline solid, gas, liquid, or amorphous material. It's similar to XRD, but radiation in that neutron radiation is there. So you have to give it gives a complementary information. You can see here you have a sample is here and you have a monochromatic neutron beam is coming. But for neutron you need a reactor source. So more high cost is involved in this case. So here once neutron is coming and falling on the crystal, and then there is a diffracted thing. So similarly to let's say 2 theta angle, you'll be able to get the particular diffraction pattern, and it also depends upon the Bragg equation you get analyze the crystal. So in neutron diffraction, so neighbors and isotope can be discriminated. Like nearest neighbor, that things can be distinguished even in same copper 64 or copper 65. So those things can be isotope discrimination is possible, which is not possible in XRD. So it can use for right element like carbon, hydrogen, those things can be detected in neutron diffraction, but it's not possible in XRD. Similarly, magnetic structure can be determined by neutron diffraction, but it's not in XRD. So in that way, it has a higher, this high high-end instruments, but it has required long time scan as compared to XRD, and its availability is much less as compared to XRD, because you need an neutron source, so you have to availability which is only possible with nuclear reactor or high energy cyclotron, those type of things. Or if you see the nuclei that once the Bragg's law is satisfied, then only you will get a diffraction, that scattering from the nuclei. The nuclei is here, that the neutron beam is fall and you will get a scattering. But in case of magnetic, what happens, there is two type of interaction come. One is nuclear scattering, one is magnetic scattering. Because in a magnetic, that vector is can be perpendicular or parallel. But perpendicular, if it's parallel, you can see this is the intensity, the nuclear scattering in this way. If you see, so these are parallel beam, so parallel spins. So you are able to see that no magnetic movement. But this is perpendicular. If you see the electron beam is falling here, and this is perpendicular, then you will able to see that Newton depth, that's kind of magnetic scattering. Here, that is mainly application for crystal structure refinement, that the nuclei scattering and structure distortion you can see. But in case of magnetic, you can able to say the spin magnetic arrangement, spin arrangement, or magnetic form factor, those things you can able to do. And here, that mainly that all the interaction is expressed in terms of Q. Q is wave vector, that here Q that 4 pi by lambda into sine theta. That whatever that earlier case is that the 2 theta diffraction Bragg's equation that used in XRD, but here the same thing is used, but it expressed in Q terminology. So if you see that in case of XRD, that form factor F equal to, it depends on the 2 pi into I into HX, KY, and LZ. So mainly it's depend on, Fn, that is the atomic, form factor. So it has dependent. So that is depend on the Z value. You can see here, if a hydrogen, carbon, nitrogen, of a cesium, you can see how bigger the heavier the atom. But in case of that type of dependence, it's not in case of neutron, you can see, but it depends on Bn, that is called scattering length. Each element has each neutron has a particular element's neutron has a particular scattering length. You can see that is randomly varies. For example, you can see hydrogen is quite bigger, lithium is small, and suddenly that sulfur is small, but zirconia is large. So it doesn't depend on the Z number of the element. So it's mainly depend upon the how much the scattering capability of that particular element. So if you see the form factor in case of X-ray, it's decreased like this, but neutron, that magnetic interaction which I discussed, that falls much faster. But if nuclear interaction, there is not a significant fall. So that's why if you see, then a normal XRD, so your high initial peaks are quite large, but higher there is decrease. But it is in case of XRD, but in case of neutron diffraction, these peaks are random, like possibly in higher angle, it can be small or less. So that's because that it doesn't have a form factor dependence in here. So you can see the X-ray, you can able to identify few things, but those are not possible in XRD. Those information you can able to get in neutron diffraction. As I discussed earlier, that KCl and NaCl, in KCl you have less number of peaks. Here 111 peak and 311 peak is absent in case of X-ray diffraction. That is told in X-ray that K and FCl, since they are isoelectronic, so this factor is quite low. So you're not able to Fk minus FCl is almost 0. These peaks will be overlap. This peak will not be seen in case of KCl. But in neutron, the scattering length of these two elements, potassium, scattering length of potassium is 3.6 FM, but that of chlorine is 9.5. So there is a much difference, and this ratio will get 0.48 B K minus BCl by Bk plus Cl. So it's quite high. So because of that, you can see you are able to see these additional peaks. Those are not seen in case of XRD. So those information you can able to get here. So in that way, it's better for crystal analysis. Similarly, there an example I have shown here, that is Ni Ni3Mn. So you can see here in Ni3Mn that XRDFS scale, we are all even, that's almost cancelled out in that, but here otherwise you will get BMN, MN minus BNI. So polarity structure, because of this high value in case of neutron, that scattering length ratio, so you'll be able to get better information. Similarly, Ni3Fe, then another example here, you can see that with if you go for nickel substitution with nickel 60, that even neutron natural nickel VNI factor is here is 0.02, but in case of Ni60, that found the scattering length is quite small in case of normal nickel, natural nickel 2.8, and this is 10.3. So because of that, you have a quite large, ratio with this ratio. So because of that, you can identify the isotope effect in case of neutron analysis. So, but in case of magnetic, if you have a parallel, that will not contribute to the magnetic contribution, but if a perpendicular, you will get that magnetic interference, magnetic interactions. So only magnetic moment perpendicular to the Q vector will be contribute to the magnetic scattering length. Like for example, you have ferromagnetic material, you can see because of this magnetic scattering, that it will be added additional to the peak intensity can be increased because of this. So the antiferromagnetic, you can able to see some peak which are not normal exactly those things information will get. You can see here, this is a ferromagnetic interaction. So all are spin are towards up direction. In that case, you can see you are getting some additional enhancement in the intensity in case of neutron diffraction. But you could go to antiferromagnetic, there some are up and some are down here. Then you can see there are antiferromagnetic coupling, this A and B, that is. So what will happen? Then you can see some antiferromagnetic because of that, some additional peaks you will able to get in that case. So here you can see that MNO, an example that is a superlative structure that of antiferromagnetic material MNO, FeO, Ni below a particular Nil temperature. These are antiferromagnetic. You can see that some spins are up and some spin are down here because of the antiferromagnetic interaction. What happened in X-ray, but you are getting some peaks you are getting, so that that antiferromagnetic, once you go down to low temperature 80 K, it is a room temperature neutron diffraction. You can see once you go down to below 80 K, that is the below Nil temperature, where MNO behaves as an antiferromagnetic material. You can see that one peak here, and you can see the additional peaks. You are able to get many, whatever that those peaks you will able to get. So you will get an information about antiferromagnetically coupled things which you don't get in case of XRD. So those type of information you will able to get in antiferromagnetic material. But neutron diffraction has a drawback that you need neutron fluxes are quite low as compared to X-ray. So you need the experiment has to be quite longer time to get this information, and then the same time you have to large sample you need for powder diffraction. At least you need few mg, or if you go to the gram scale, it will be much better results. But in case of single crystal, you have 5 mm to 1 centimeter cube. But in case of this neutron diffraction, this much large quantity of sample, 2 to 3 gram of sample you need for neutron diffraction analysis. And neutron observing like cadmium, gadolinium, samarium, or boron, those are observed neutron. So those type of element is not possible to analyze by the neutron diffraction, and you still have to go for a major facility like reactor or spallation source to do all type of neutron diffraction analysis. So if you see in comparison to X-ray diffraction, neutron diffraction will give some complementary result. You can get some more information which you are not possible in case of XRD, but at the same time it has lots of drawback. You need X-ray in this spallation source or reactor source, which is not easy to do. But at the same time you get better information with neutron diffraction using magnetic structure especially. So if you see that what we discussed in today's take-home message, it's mainly we studied single crystal XRD. So that will mainly use for 3D electron density mapping. The atomic arrangement you can able to find out using single crystal XRD, and by using grazing angle XRD, you'll able to find out the thin film analysis, or depth profiling. You can layer by layer structure and intermetallic that growth. Those things can be identified using synchrotron radiation. You get by synchrotron XRD, you get better information. Even at trace levels, you can perform high temperature, high pressure measurements, as well as EXAFS absorption spectroscopy. where X-ray absorption fine structure either using near edge, band edge, or X-ray extended X-ray absorption from fine structure. We'll be able to get information about nearest neighboring atom, coordination numbers, as well as valency structure and oxidation states. Those things you can find out. But in case of XRF, X-ray fluorescence spectroscopy, you are able to analyze, get the compositional analysis, what is the concentration of each element present in the particular system. Those things you can identify in case of XRF. But in Newton diffraction, you can be able to get atomic and or the magnetic structure of a crystalline materials, which is complementary to the XRD technique. So today I have mainly discussed all these techniques. So in next class, we'll discuss about scattering. So the X-ray absorption, X-ray diffraction, those and X-ray fluorescence we'll discuss. So then we'll discuss X-ray scattering and neutron scattering. Like Newton X-ray diffraction, this X-ray and neutron can be scattered from a bigger molecules. So whatever we study, that those are mainly, this X-ray diffraction and neutron diffraction deals with the atomic level study. For a neutron scattering or X-ray scattering, that is small angle neutron X-ray scattering studies, those are particles. We will study how the particle size and all these things information in next class. If any questions, you can raise now. If there is a question, is there any software available to interpret X-ray data? Yeah, there are many software like the one software is the X-ray Pro that those type of the routable analysis software at full. Those are coming with XRD instruments, so there you can use those type of foolproof like software. Then, but that free is there are few software available. That is one is X-ray. I'll discuss that software. I will tell you then the next class. For those even I will provide you with those softwares links. That one is the Excel analysis, that Excel something that is available. So that is free. Otherwise, you will able to get that full software from the X-ray instrument that can be used in case of X-ray analysis. So other one, the free one, I will tell in the next. I'll give the link of that so that you can download and use it for your analysis. Okay, since there is no more question, we can close today's lecture here.